Imagine a vast, empty space stretching out forever. The vacuum of space, a seemingly barren void, silent and empty. But what if we told you this nothingness holds one of the most perplexing mysteries in the universe? Welcome to the vacuum catastrophe, a paradox that has haunted scientists for decades. According to quantum physics, even in the deepest emptiness of space, there's a seething sea of energy, constantly fluctuating as particles appear and disappear in the blink of an eye. When scientists calculated the amount of this vacuum energy, the numbers didn't just seem wrong, they were off by a factor of 10 to the power of 120, a number so massive it defies comprehension. This gap between theory and observation became known as the vacuum catastrophe. How could our calculations be so wildly incorrect? Why does the universe even exist if the vacuum energy should be infinitely strong, tearing everything apart? Some physicists suggest we're missing a piece of the puzzle, a hidden law of nature yet to be uncovered. Others think this catastrophic miscalculation points to something deeper, as if reality itself has secrets it refuses to reveal. Is this vacuum catastrophe a clue to a higher truth? Or is it simply a reminder of our limitations, that we're peering into a cosmic void we may never fully understand? One thing's certain, the answers lie somewhere in that silent, unseen energy that fills the dark spaces of the universe. And as we search, the question remains, how much more is hidden in the void, waiting to be uncovered? Could the very nature of time itself be tangled in this cosmic puzzle? What if this hidden energy, lurking in the depths of space, holds the key to the time paradox? In our vast universe, the speed of light serves as a fundamental limit for how quickly anything can move or any process can occur. Even on a tiny molecular level, information is transmitted at the speed of light. But we still haven't measured it. We only have data on the two-way trip, which involves bouncing light off a mirror to calculate its round trip time. So it's just an assumption that the speed of light is constant in both directions. But what if it's not? One day, an important message is sent from Earth to the first Mars settlers. The message reads, "This signal was sent at midnight. Adjust your clocks accordingly." We know the speed of light takes 24 minutes to reach Mars and return to Earth. The Mars settlers assume that the one-way speed of light is exactly half the round-trip speed, and adjust their clocks to 12 minutes past midnight upon receiving the message. But in this scenario, light traveled at only 50% of its usual velocity to Mars, so it took 24 minutes to reach the red planet. Unaware of the discrepancy, the Mars settlers respond, "Clock adjusted, message sent at 12 minutes past midnight." Meanwhile, the signal on its way back to Earth travels instantaneously. Earth's clock now shows 24 minutes past 12 when scientists receive the message. They assume it took 12 minutes for the Martian signal to arrive, so they think everything went well, even though there's a 12-minute time difference. So you can see by this example that understanding the speed of light is crucial to unlocking the enigmatic nature of time. But what exactly is time, and how do we define it? When we think of time, we imagine the changing of the seasons or see it as a handy tool that helps us agree on when and where we're going to meet someone. Although that ticking clock is just another representation of movement, the movement of our planet around the sun, to be precise. The problem is, moving through space and time doesn't seem to be governed by the same rules. There's a limit on how fast you can go in 3 dimensions of space, and that's 186,282 miles per second. But is there such a boundary for how fast or slow time can progress?